Yeah, so maybe let's continue with the second part of this session. The next paper is Super PAC, Dishonest Majority MPC with Constant Online Communication. So this is a work by Daniel Escudero, Vipul Goyal, Antigoni Poligroniadu, Yifan Song, and Chen Kai Wen. But none of them have come. So then we have a guest star, Peter Scholl, who will present the paper.
Thanks very much for the introduction. So yeah, unfortunately, none of the authors of the paper could make it to the conference, so I'm presenting this instead. So Super PAC is on a secure multi-party computation protocol, where we have a set of parties who want to securely evaluate some function on their private inputs. And the specific MPC setting in this talk is secure computation of arithmetic circuits over some finite field, and it's in the dishonest majority setting. So we have a constant fraction of the parties who may be corrupted. So there's some parameter epsilon, which is less than half, and we assume that at least epsilon n parties will be honest in the protocol. And the goal is to achieve malicious security with a bot. And the main result in this work is a new protocol in this setting where the total communication cost is a constant number of field elements per multiplication gate across all of the parties. And the constants in this work are pretty good. It's quite practical and focused on being something you can implement. And the nice feature about this constant communication cost is that if you fix the number of parties n, and imagine as the number of honest parties in this protocol increases, as epsilon increases, then the communication cost actually decreases proportional to 1 over epsilon. And the protocol is divided into these 3 phases, the online phase and 2 preprocessing phases, where the first preprocessing phase is independent of both the inputs to the computation and the circuit being evaluated, but this one has linear cost in the number of parties, whereas the second preprocessing, which only depends on the circuit, has, again, constant communication, like the online phase. OK, so in this dishonest majority setting of MPC, I guess most protocols tend to focus on the harder case of n-1 out of n corruptions, but this also tends to be less efficient. So this is things like the speeds protocol. And in this case, if you want to adapt these protocols to the less than full threshold setting, then it seems like the best thing you can do is just to remove n-t-1 parties and run the protocol among the remaining t+1 parties. But if you want to do better than that, perhaps the most relevant work is this GPS 22 paper from last year, which also gets a constant total communication per multiplication gate, but with much worse constants, so it's something that's not quite so practical. One other relevant line of work is this tiny keys protocol in a similar setting, but for Boolean circuits. But there, the focus of optimization is more on the preprocessing protocol, and the online phase still has linear communication. And finally, there's another paper last year called Turbo PAC, which is in the honest majority setting, but also has constant communication in the online phase and uses similar techniques. So the most relevant work to compare with out of all of these is one of the latest incarnations of the speeds protocol called Turbo Speeds. So here you can see how that compares with Super PAC. And notice that for Turbo Speeds, each of the 3 phases have linear communication in the number of parties, whereas Super PAC has this constant for the online and circuit-dependent phases, and in the circuit-independent phase is pretty similar to how Turbo Speeds looks, roughly 6n multiplication, field elements per multiplication. So you can see this a little more in detail on these graphs. So here in the graph on the left, you can fix a particular epsilon. For instance, if you have 10% of the parties being honest, and then you can see that if you have an MPC protocol with at least n is 34 parties in total, then Super PAC will outperform the best previous speeds protocol for all values of n larger than this. And for another data point, if you increase the number of honest parties to 30%, then you only need 15 parties before Super PAC starts becoming worthwhile compared with other protocols. And likewise, you can look at the graph on the right where you fix the number of parties, for instance, to 32, and then look at what's the smallest epsilon you can get away with, such that this protocol is worthwhile, and in this case, it's 26%. And so those graphs were for the online phase. If you look at the pre-processing phases, then it's a bit different, because here, both of the protocols have linear communication cost, reflected by the straight lines in the graphs. But the thing to look at is, so the blue lines here are super PAC, and notice that they're often a little bit worse than the communication costs for turbo speeds, but not by a huge amount, and in fact, sometimes a little better when the number of parties is very large. So you're not paying a huge cost in the pre-processing to get this benefit of a constant communication online phase. The authors also implemented most parts of the protocol and ran some benchmarks, which you can see in this table. So the bottom two rows of the table are just the theoretical communication costs, measured in terms of the improvement factor compared with turbo speeds. So here you can see that it has, in practice, around 2 to 6 times less communication than turbo speeds for, say, 32 or 80 parties. And then, of course, the question is, how does this translate into real-world performance improvements for the implementation? And if you first look at a high bandwidth network setting, it's not so great. It's sometimes a little bit slower than super PAC, than turbo speeds, sometimes a little bit faster. But as you restrict the bandwidth to lower bandwidth settings, say 100 megabits or 10 megabits, then you start to get much better performance improvements compared with turbo speeds. So here in the 10 megabit setting, you have around 2 to 6 times improvement, which pretty much reflects what you'd expect from the theoretical communication costs, showing that here communication is really the bottleneck. Okay, so for the rest of the talk, I want to give an overview of the main ideas in the protocol. So super PAC is based on packed secret sharing, which is a variant of Shamir secret sharing, where instead of secret sharing a single field element at once, we'll share a vector of k field elements, v1 up to vk. And we'll do this by sampling a polynomial of degree d. And in practice, the protocol uses different values of d at different places. So this is a parameter. And it does this based on some evaluation points. First, k evaluation points alpha 1 to alpha k, which are used to encode the messages being shared, vi, as at the polynomial. And then the polynomial is sampled to be of degree d, random apart from these evaluations. And then to define the shares, you do exactly as you do in Shamir sharing, where you define n evaluation points beta 1 to beta n, and give to party I the value f of beta I. And the nice thing about this packed Shamir secret sharing scheme is that even though you're secret sharing a vector of up to k field elements, the size of each party's share is just a single field element. So then in the protocol, the online phase has an invariant which is maintained throughout the circuit evaluation, which is that at each wire, say a wire indexed by some index alpha, if this wire has the plaintext value v, which is the actual value of the computation at this point of the circuit, then we associate with this wire a special random mass called lambda, which is not known to any parties and will in fact be secret shared in some flavor of packed secret sharing. And we use this to define a masking of the plaintext value v as mu, which is v minus lambda. So this could be given out in public, but for efficiency, mu is just given to party P1. And note that at this point, for each wire, the plaintext value v is entirely determined by mu and lambda. Okay, so given this setup and the idea that we're using packed secret sharing, the main challenge in any MPC protocol where you want to exploit packed secret sharing is that, okay, you naturally will want to evaluate, say, k multiplication gates in parallel on packed secret shares. But then as you go through the circuit from one layer to the next, you often need to reorder these elements of packed secret sharings to match the wiring of the circuit, which unless you're doing a pure SIMD circuit, will require some kind of routing or permutation protocol. And that's kind of the traditional approach to doing this with many older works. But the nice idea of this protocol is to follow some methods from the TurboPack protocol in the honest majority setting, which gives you a way to maintain this wiring consistency with very little overhead and without having to do any complex permutation networks. So to do this, we'll rely on this circuit-dependent preprocessing phase, which will set up special sharings of the lambda masks across the circuit. And so you divide each layer of the circuit into batches of k multiplication gates, which will be evaluated in parallel. And then you take the batch of, say, left input wires and right input wires for each of these batch of multiplication gates, and then prepare them using packed secret sharing. So you take the vector of lambdas and distribute packed shares to the parties for these random lambda values. So this requires a bit of interaction. And then in the online phase, when you have this setup, you evaluate these gates in the same batch of k gates at once. And by exploiting the fact that, according to this invariant we defined, P1 will always know these mu values in the clear for every wire alpha, then it can just kind of collect the right set of mu values which are needed for this set of wires and use these to help with the multiplication protocol without any fancy routing process. So going into this in a bit more detail, so if we have a batch of k multiplication gates with inputs, input wires alpha and beta, and we have these corresponding masked values mu for mu alpha and mu beta, which are known to party P1. And in the first part of the protocol for the multiplication gate, P1 will take these and distribute fresh Shamir sharings or packed Shamir sharings of degree k-1 to the other parties. So note that this is the packed Shamir sharing of k elements of degree k-1, so there's actually no randomness in this polynomial, but it doesn't really matter because these mu values are public anyway. So the idea of the Shamir sharing here is just to kind of optimize the communication. And then from the invariant for the input wise of the multiplications, and also from the preprocessing, we have these lambda values all secret shared with packed sharings. So the lambda alphas, the lambda betas, which will be of degree n minus k, and then the lambda gamma, which will be of degree n minus 1. And then also this special value capital gamma, which is the product of the input lambdas, which will be computed in the preprocessing using some packed multiplication triple. And given all of these shared values, you can see that the parties can actually just take an appropriate combination of these by doing some local multiplications and summing them up, and they will end up with a packed sharing of degree n minus 1 of the right vector of the mu values for the output wire. Once all the parties have this, they can just reconstruct it to P1, who will learn the mu value, and then maintain the required invariant. So this is a kind of simplified version of the basic protocol, which is at this point only passively secure. There's one more change that is made in the final protocol, which is an optimization to reduce communication, that this interaction in the basic multiplication protocol is combined with the interaction in the preprocessing used to create the product of the secret shared values with beaver multiplication. So the details aren't important, but that saves a bit of communication. But now the main challenge at this point is to add active security. So if you recall, there are these two openings in the protocol where first P1 distributes shares of the mu values, and then the output mu value is opened back to P1. And there was nothing in the passive protocol which ensures these things are done correctly. And the solution the authors use in this work is to apply a secret shared information theoretic max to make sure that these sharings are generated and reconstructed correctly. And so for this, we use two additional types of sharings. One is standard additive secret sharing, denoted using angle brackets here. And another is a special kind of packed Shamir sharing where you just secret share a single scalar, here V, and then kind of pack it into the ith slot of a packed secret share where all the other slots can be just random and you don't really care about it. And these are used to extend the invariant in the passive protocol by adding on some additional authentications of the appropriate values. So as well as the mu value, which is known to P1, and the lambdas, which are secret shared with packed Shamir sharings, we now have authentications of both the mu and the lambdas. So these are additive shares of each mu component and additive shares of each lambda component multiplied by delta, where delta is a random field element which acts as a secret MAC key known to no one. And also as a kind of one-time global setup, you have these special Shamir sharings of delta packed into the ith coefficient of the slot, which helps with the multiplication protocol. And so this is the invariant, which of course you want to be maintained after multiplication, so you get the same property on the outputs. And so quickly going through, so the final protocol with active security turns out to be roughly the same as the passive secure one, just with the addition of these MACs. The idea is that when P1 distributes the packed sharings of the mu values at the start of the multiplication gate, the parties will use some MACs which they have to be able to verify that these mu's were distributed correctly. And based on the invariant and the preprocessing, we'll have these additional MACs used to do the check, and also used by taking some appropriate combinations of them to ensure that we can get the MAC for the output mu value used to the next gate. So I think I'll skip over the technical details here, but basically there is some like nice conversion tricks for converting from special types of Shamir sharings to additive sharings, which you can exploit to get this kind of multiplication and get the MACs to work out in the output. So that's all I wanted to say for this talk. Thanks for your attention.
So if there are any questions, Peter can try to answer them, even though he's not an author. So, I mean, one thing I was wondering is this for any field, or is it like large enough fields, or?
It should be a large field for the MACs to work out. It could be that you can make it work in small fields with bigger MACs, but I'm not sure if they do that in the paper.
But also there's Shamir secret sealing being used, so are they like?
Well, it should be at least as large as n plus k or something. Mm-hmm. Yeah, so not over f2, for instance.
Okay. Yeah, if there are no more questions, then let's thank Peter again. And the last talk is called Detect, Pack, and Batch, Perfectly Secure MPC with Linear Communication and Constant Expected Time. It's a work by Itai Abraham, Gilad Asharov, Shravani Patil, and Arpita Patra, and Shravani is going to give the talk.
Thank you for the introduction. Hello, everyone. Today I'll be talking about our work on the communication complexity of perfectly secure MPC protocols. So let me begin by introducing MPC, or multi-party computation. MPC allows n mutually distrusting parties to compute a joint function of their private inputs. Now, this distrust among parties is typically modeled as a centralized adversary, which can corrupt up to T out of the n parties. And the goals of any MPC protocol are correctness, that is, the protocol output should be equal to the function output, and privacy, that is, nothing beyond the function output should be revealed to the adversary. Now, based on various parameters such as the threshold of corruption, the nature of the adversary, and so on, there are various settings which have been considered in the literature, and in our work, we focus on one such setting, that is perfect security. Here, a threshold of T less than n by 3 is known to be necessary and sufficient. The adversary is unbounded powerful, and there is zero error probability in the output computed. Okay? So in our work, we focus on perfectly secure protocols with malicious corruptions, and primarily we focus on the communication complexity. So looking at already what exists in the literature, first from the broadcast hybrid model, we see that broadly there are two categories of protocols. One which we refer to as efficient but slow, and the other one, which we call as fast but inefficient. Let me make this clear. So the first category of protocols, which we call as slow, are the ones where the round complexity actually depends on the number of parties involved, n. And the second category, which we call as fast, is where the round complexity is independent of n. Now, what we observe is that in the first class of protocols, following a long line of work, the state-of-the-art work of Goel, Liu, and Song achieves a communication complexity that is linear in the number of parties per gate. However, the scenario in the second category of protocols is very different. Here, to evaluate each gate, there is a n power 3 amount of communication over point-to-point as well as broadcast channels required just for a single gate. So a natural question that we see is, can we get the best of both these approaches? That is, can we get a linear communication complexity per gate while ensuring round complexity that is independent of n? And in our work, we answer this in the affirmative and give an efficient as well as a fast MPC, as we call it. So just to be more clear, we look at this from the point-to-point model, that is when the broadcast channel is instantiated with a broadcast protocol. So we see that broadcast in itself can be instantiated with two different classes of protocols. One is where the protocols are deterministic, order of n round protocols, and the other one where the protocols are randomized and they give expected constant round complexity. So we observe that using both the kinds of protocols for broadcast, the work of Goel et al. Has a communication complexity that is linear per gate, whereas the work of the state-of-the-art work of Abraham, Asherov, and Yanai has a round complexity that is order of d, that is independent of n. The important point to note here is that none of the prior works achieve both the good features, as we call them, together. And our work is the first one to achieve this linear communication per complexity per gate and order of depth round complexity for large enough circuits. So coming to our main result, we give an MPC protocol which has a communication complexity of order of Cn plus Dn squared plus n to the 4 over point-to-point channels for evaluating a circuit with C gates and depth D. So looking at it from the broadcast hybrid model, we have a point-to-point communication of the same order and a broadcast communication of n cube, and each party does n squared communication here. And to instantiate this, we use the broadcast protocol of Abraham, Asherov, Patil, and Patra, which allows us to achieve expected order of depth round complexity. Coming to how we achieve our result. So at a very high level, we follow the Beaver circuit randomization trick to get our MPC. But in particular, we follow a framework which was formalized in the work of Chaudhary and Patra. So here, there are n parties, and each party starts off by using a verifiable secret sharing, VSS primitive, to share random multiplication triples. So once this is done, given that parties are malicious, the multiplicative relation might not really hold, and we need to verify this. This is where the second component, that is the verifiable triple sharing, comes into the picture. And this does the verification of whether the multiplicative relation in the triple actually holds or not. So the outcome of this primitive can either be a success, that is the proof goes through, or it fails. And in case of failure, we can simply discard the triple shared by that party. Following this, a triple extraction primitive takes in the triple shared by all the parties and gives out random multiplication triples which are unknown to any party. So this together forms the Beaver triple generation phase as we know it. And following this, we can have a Beaver multiplication going on, which will just consume these triples to actually evaluate the circuit. So what we observe is that if we have an order of n communication complexity protocol for each of these primitives, then we can get an order of n complexity MPC protocol. And from the literature, we have that the triple extraction and the Beaver multiplication protocols, or Beaver multiplication primitives, already have such protocols from the work of Chaudhary et al. And Damgard Nielsen. So what remains is the VSS and the verifiable triple sharing primitive. And this is exactly what the contribution of our work is. So before moving on to the exact contributions, I'll go over the key design principles that we follow in this work. And they are as follows. The first is packing. So since we primarily deal with sharing of secrets in the form of triples, in order to ensure a low cost, we first pack secrets in a single instance of sharing so as to amortize the cost. Secondly, we observe that broadcast communication is what causes the primary bottleneck in terms of the communication complexity. And hence, we use our second principle, that is batching of the broadcast cost across multiple instances of the sharing. And finally, while designing these protocols, it so happens that the corrupt parties can, in some sense, create failure. I mean, they let at some times, do not allow the protocol to terminate successfully. And in this case, we use our third design principle, that is detection, wherein we identify corrupt parties and neutralize their power to further obstruct the successful completion of protocol. So coming to the first primitive where we have a contribution, that is verifiable secret sharing. So VSS is a primitive, which is a two-phase primitive consisting of a share and a reconstruct protocol that allows a dealer to share secrets amongst the parties with the following properties. The first one is hiding. That is, at the end of the sharing phase, the adversary will not gain any information regarding the secret of an honest dealer. Then we have binding. That is, at the end of the sharing phase, there is some secret that is committed to, and this is defined by the view of the honest parties. And finally, we have validity or correctness. That means that at the end of the reconstruction phase, the secret that has been committed to will be the one which will be opened. And when the dealer is honest, we have that the secret is actually the one that the dealer shared. So coming to our main result for the VSS, we give a VSS scheme with perfect security and optimal resilience, which has a complexity of order of Pn plus n power 4 over point-to-point channels for sharing P secrets in expected constant rounds. So what this essentially means is that when we have large enough number of secrets, then we get a linear overhead per sharing of a secret. And this exactly matches the semi-honest secret sharing, where a dealer would simply hand out shares to each party. Okay. Comparing with the existing prior best known VSS of Abraham et al., what we see is both our VSS as well as their VSS in a single instance shares order of n secrets, and in fact at the same cost. However, we differ in the design principles that we use. So the work of Abraham et al. Primarily uses the packing design principle. So you can think of this as an array of order of n secrets packed along the x dimension of a bivariate used for sharing. Whereas in our work, we use packing as well as detection of corrupt parties. And this helps us in getting a better cost when we run multiple instances together. So the key difference here lies in how we choose our bivariate polynomial. We choose the degree in such a way that it allows us to balance the broadcast communication done by each party, in contrast to the work of Abraham et al., where the dealer used to communicate order of n factor more than each other party. So the way this helps us is when we run multiple instances of our VSS together. So while the work of Abraham et al. Continues to use the principle of packing, in our work, we can use packing, batching, and detection. So note that here, we managed to get the same broadcast cost, that is order of n squared, as we required for one instance of our VSS, whereas in the case of the prior VSS, the broadcast cost depends on the number of instances that you're executing. This shows up in the final complexity of the protocol, wherein we get a linear communication complexity per secret, whereas the prior work achieved a quadratic communication complexity. So this summarizes our contribution in terms of the VSS. So looking at the big picture again, what now parties can do is share each secret using our secret sharing, and this will be shared with a degree T, as we require eventually. And now the goal is to verify that the product relation of the triples that they've shared indeed holds. And one way to view this requirement of the triple sharing is in the following way. So a party trying to prove that its multiplication relation holds requires to share, in some sense, order of n secrets. Now, even if we use the VSS that I just defined, which has a linear cost, this would amount to a quadratic cost just to verify a single secret. And this is beyond what we can afford to get linear complexity MPC protocol. And here is where our second contribution comes into the picture. So we identify that we don't need a full-fledged VSS to prove the relation, rather a weaker notion suffices. And in our work, we formalize this weak notion, which we call as detectable secret sharing. So detectable secret sharing, similar to VSS, is a two-phase protocol, which has a sharing and a reconstruction phase, and it allows a dealer to share secret with all the parties and with the following properties. The hiding and binding are exactly the same as that what you get in VSS. However, there is a difference in the validity property. While VSS allowed the reconstruction to always succeed, in our case, it might not so be the case. In fact, for us, one of the following two conditions holds for our validity property. So the first one is that the reconstruction indeed succeeds. And in this case, what we actually have is the properties of a VSS protocol, if this case happens. On the other hand, it is possible that our reconstruction also fails. And if it does so, we make sure that our third design principle, that is detection, comes into the picture. And an honest dealer who is trying to share the secrets will identify at least order of n corrupt parties and make sure that they cannot further obstruct the successful completion. So coming to the result in detectable secret sharing, we give a protocol with perfect security and optimal resilience, which has order of p plus n to the 4 communication for sharing p secrets in expected constant number of rounds. So note that this amounts to a constant overhead per secret when p is large enough. And this matches packed semi-honest secret sharing in contrast to the standard semi-honest secret sharing, which our VSS was matching. So now if you think about the triple sharing, which essentially required n secrets to be shared for the proof, if we use our detectable secret sharing, we are still within the bound of linear complexity, which we aim for. So contrasting our VSS with the detectable secret sharing, we see that a single instance of our VSS as well as detectable secret sharing has the same complexity, and in fact, both use the principles of packing and detection, but the difference is in the way the packing is done. So while for VSS, we were packing along just one dimension of the bivariate used for sharing, in case of detectable secret sharing, we pack order of n secrets along both the dimensions. So you can think of this as a matrix of values which is getting packed. And this is what allows the detectable secret sharing to simultaneously share n squared values in contrast to order of n which was getting shared in the VSS. Analogously, in the case of running m instances together, we see that our VSS uses packing, batching, and detection. And similarly, the same principles are used by the detectable secret sharing as well. And the important part to note here is that just like VSS, our detectable secret sharing also has a broadcast cost that is independent of the number of instances that we are running. So just to summarize the design principles, in our work, we have used packing, batching, and detection to get primitives such as VSS and a new primitive called detectable secret sharing, which finally allows us to get a linear complexity MPC protocol. Compared to with respect to improvements compared to the state-of-the-art works, for VSS, we have an order of n factor improvement compared to the work of Abraham et al. And for the triple sharing primitive, our work improves the state-of-the-art by order of n cube. And this finally allows us to achieve the linear communication complexity that we aimed for. Thank you.
Are there any questions? I was wondering where does this expected number of rounds come from, and if there is any chance of like improving that or.
Oh, so the expected is coming out from the broadcast protocols. So all the results I've described are mainly in the point-to-point model. And getting broadcast with strict constant number of rounds is known to be impossible due to work. So either you go for order of n rounds or expected constant round.
Okay, that's also for the detectable secret sharing. You also need the.
Yes, yes.
Okay.
Thank you.
Any other questions? Okay, so then let's thank the speaker and all the speakers of the session again.